So our project is going to be focused on the soleus muscle, which is a calf muscle found in your lower leg behind the tibia bone, which is the largest bone in your lower leg and is basically your shin bone. So there's also another calf muscle that you have in your lower leg called your gastrocnemius, which itself has two heads, the medial head and the lateral head. And both of these calf muscles are attached to the calcaneus bone or heel bone via the Achilles tendon. And the gastrocnemius connects to both your heel bone and your femur. This diagram is basically like, imagine like these muscles are cut like halfway, because they actually do extend up more, but it's just so you can see the relation of the muscles to each other. But they do extend up more, so the gastrocnemius actually does connect to the femur, but the soleus does not. It instead connects to the tibia bone and the fibula bone, whereas the gastrocnemius does not connect to either of those. Yeah, and so the soleus muscle is a plantar flexor, which means it's in charge of motions like pointing your foot, extending your toes, and then generally just stabilizes your tendons when they're under force. So it's very important for absorbing contact and like landing on the ground, stuff like that. So since your soleus is a skeletal muscle, I thought I might draw a simple diagram of a skeletal muscle. So basically, it's connected to your bone via a tendon, which is, pretty much just a connective tissue that, connects bone to muscle. And then there's a connective tissue that surrounds the entire muscle called the epimysium. Within the epimysium, you have multiple things. You have fascicles, which are basically bundles of muscle fibers, and then you also have blood vessels, which are in charge of basically carrying blood throughout your muscle. And within the fascicles, you have the endomysium, which is another tissue that surrounds each of the individual muscle fibers. And then there's also a membrane called the sarcolemma that surround each individual muscle fiber. And then within the muscle fiber, the muscle fibers are called myocytes, but within each myocyte there are myofibrils, which are basically bundles of protein filaments that have like a lot of the contractile elements of the actual muscle fiber.
Now it's time to discuss the physics of this ankle joint. How does it do its job, and how does it utilize the laws of physics to do this more effectively? We can model the action of the soleus muscle using a second-class lever, in which the load is between the fulcrum and the effort. In this case, the effort is applied by the soleus muscle right at the heel, and the load is the body weight applied by the tibia. The fulcrum is the ball of the foot. When the soleus muscle contracts, it exerts a rotational force around the ball of your foot. And if you've ever pushed open a door, you'll know that pushing farther from the hinge creates a larger rotational force. So therefore, we can write that the torque or rotational force created around fulcrum is equal to the radius that force is exerted over times the magnitude of the force. And we should notice that the soleus exerts its force at a much greater radius than the load exerts its rotational force. So the soleus, therefore, has an advantage for creating torque around the ball of your foot. This advantage is called mechanical advantage, and it is equal to the ratio of the input radius over the output radius. Mechanical advantage refers to how much an input force is multiplied by in a simple machine. In this case, the simple machine is a lever. So the input force of your soleus muscle is effectively being multiplied by this mechanical advantage factor to get the output force on the load. Alright, so I've done some measurements and I determined that the small radius of my foot is 0.12 meters, the large one is 0.19 meters, meaning the mechanical advantage of my foot is MA equals 0.19 meters over 0.12 meters equals 1.6. Now let's do a quick calculation to figure out whether this is actually the mechanical advantage of my foot. So we're going to start with this equation for the sum of the torque. The sum of the torque on my foot is equal to the applied torque from the soleus muscle minus the torque from the load of my body weight is going to be equal to the moment of inertia of my foot times the angular acceleration. And so we're going to simplify this and say we're at an equilibrium state where the torques cancel out. So this is going to be equal to 0. So now we can expand this to solve for applied force. So now we can plug in our values. I estimated my mass to be 56 kilograms, and now we can solve. So plugging these into the calculator, we get 346.9 newtons. Okay, so that was our input force, 346.9 newtons. Our output force is simply going to be our body weight. So that's going to be mass of the body times G. Which is going to be 549.36 newtons. Okay, so then does this match up with our previous estimate of mechanical advantage as 1.6? And the answer is, well, yes it does, because the mechanical advantage in terms of the force is going to be the amount by which the force is multiplied. So it's going to be the output force over the input force. And in this case, that is going to give us a ratio of 1.6. Mechanical advantage is indeed equal to the input radius big R over the output radius little r. From this we can conclude that our foot has a significant mechanical advantage, allowing us to move our entire body weight with just a single flex of the muscle.
Race walking is an exhilarating sport that's like distance running, but with more distance and less running. The main advantage of race walking over distance running is that it supports the job market, employing referees to enforce its strange rules, which are as follows. 1. One foot must always be in contact with the ground. 2. The planted foot must not be bent from the moment it touches the ground to the moment that it is lifted again. While it may seem from the demonstration that I do not know the second rule, I was actually simulating what would happen if a judge were distracted and a competitor was able to achieve an unfair start. We chose to analyze race walking rather than marginally more interesting sports like running because the static nature of the movements make it easier to isolate specific muscles such as the soleus. Specifically, we focus on the role of the soleus in pulling the trailing leg, and then again in absorbing the ground reaction force.
Okay, so there's already been a video of professional race walkers. However, Damien and I decided it would be a good idea to do a demonstration of us race walking. So, we have a video of that playing in the background where I'm going to explain a little bit about how it looks in the stride, in the race walking itself, how that looks for the muscle, the soleus muscle. So, first off, you have liftoff, and that is of the trailing foot. And we can see this in the video, and we can see that the soleus is experiencing the concentric phase of contraction. That means that the muscle is shortening in length during this contractionary phase, and it's concentric. And then immediately when, or right before, that trailing foot lifts off the ground, Now there's the heel impact of the front leading foot. Now this is the eccentric phase of contraction of the soleus, as it absorbs energy that comes through the heel from the Achilles tendon. Now this eccentric phase of contraction of the soleus is where under tension the muscle is now lengthening. So these are two different types of contraction, however they serve different purposes, and of course concentric is when the muscle is shortening, and eccentric is when the eccentric contraction is when the muscle is lengthening. And in both of these cases here, in the stride, while walking, the soleus is putting in some sort of work and is contracting and using energy in order to lift off and then also absorb heel impact in a later step. Okay, so overall in walking, or more specifically in the sport we're analyzing, race walking, the vertical ground reaction force that goes through the leg that the foot initially comes in contact with is around 1.2 times to 1.5 times your body weight. Now in this case, the body weight is not just the mass of the person, like 145 pounds, but rather it's mass times gravity, and you multiply that value around 1.2 to 1.5 times for walking. Now it's important to note that with something like running, the ground reaction force is more like 2 times or up to 2.9 times a person's body weight, and an even greater value for sprinting or even higher intensity forms of this basic motion of walking or running. So race walking has a little bit less ground reaction force compared to something like running, but it's still a significant contribution, and we see that through this is the force that's going to end up going through the soleus, and that the soleus has to absorb when the heel comes in contact with the ground.
Given the footage, we can calculate the time for a period of motion, that is the time it takes for one step with each leg. With this, we can calculate the cadence. Possibly because of my illegal second step, I was able to accelerate more quickly than Jack, completing the first cycle in 8.53 seconds to Jack's 9.13, giving me a walking frequency of 7 Hz, and Jack a walking frequency of about 6.6 Hz. Estimating the height, it looks like I raised my leg more than Jack to a height around 4 centimeters, while Jack appears closer to 2.5 centimeters. We can also estimate the weight of the leg using values from xrets.net, which approximates the weights of body parts as a percentage of total weight. In our case, we are mostly focused on the lower part of the leg, as the thigh does not move much vertically. xrets.net estimates this part of the leg to be about 4.75% of total body weight for men. This gives a leg weight of 0.31 kilograms for Jack and 0.39 kilograms for me. Using the weight and change in height, we can calculate the change in potential energy or work, specifically using mass times g times change in height. Based on this formula, Jack's work is about 1.69 joules, while my work is significantly higher at 3.36 joules, owing to my greater vertical displacement and weight. Finally, if we measure the time it takes for the movement from ground to maximum height, we can calculate the average power over the duration of the action using the formula power equals work over time. I completed the movement somewhat faster than Jack in 1.18 seconds to his 1.6, giving me an average power of 152 watts to his 103 watts. Based on this, we can conclude that taller walkers will be forced to exert more energy per step. We can also see, as we expected, that the power required is proportional not only to height, but also to the speed that a person is walking. The calculations show that Jack was able to expend less energy by having a more efficient stride with less vertical movement, suggesting that minimized vertical displacement is important for strong performance. I was able to move faster over the same period, however, perhaps suggesting that increased expenditure of energy results in increased acceleration of velocity, at least in the short term.
And that's it. We hope you enjoyed our Biomechanics Sport Report video talking about the soleus muscle, which included the anatomy and structure of the soleus muscle within the calf, the physics application of the soleus muscle that acts like a second-class lever, and the sport report done relating the soleus muscle to race walking, with a variety of calculations done to see what the soleus muscle experiences during the sport of race walking. Once again, thanks for listening.